The next example we are looking at involves an equation which has the cosine trigonometric function in it. Again, we are looking at an equation involving x and y, and if you look at this equation, you will actually realize that it's virtually impossible. It is impossible to solve this equation for y and look at it as a function in x. So we will really need implicit differentiation here to find dy by dx in terms of x and y. Before we start differentiating here, let's look at the curve of this function, because it's a rather, what I would call a quite wild function. So I've again pasted the equation of our curve into this implicit function plotter, and I'm looking at it in the range between negative 20 and 20. And that is a picture, and you realize it's what I meant when I said that that's a quite wild function. So lots of waves here. You can look at a larger range and you see even more waves. So, and you see the reason why it will be impossible to look at this as a function in x. So to find dy by dx, we'll apply implicit differentiation here to both sides of the equation. That means we apply d by dx to both sides. And as before, we treat y as a function in x in both places. So the first term here is a product of two functions, x and cos y, so we need to apply the product rule. So we differentiate x, that's 1, leave the cos y alone. We leave, for the second term, we leave x and differentiate cos y, where we need the chain rule, since it's a composition of two functions. Differentiate the cos gives negative sine y, times the derivative of the y, that's the dy by dx. And here in the second term, the roles of x and y interchanged. So we differentiate y, it's dy by dx, leave the cos x, and then leave the y and differentiate cos x. That gives a minus sine x, and the right-hand side gives a 0. So in this example, we want to solve this equation for dy by dx. So we collect all the terms which have the dy by dx in it and factor it out. So we'll have here cos x, and here we have an minus x sine y. And we'll put all the terms which do not have the dy by dx in it to the right-hand side. So we have this term here goes to the right with a positive sign, so we have a y sine x, and the cos y comes over here with a minus. So all we need to do in the last step now is divide here by these brackets, and we have solved the equation for dy by dx. And maybe I'll write this result here with a negative sign in front. That means we get here an x sine y minus cos x. And you see sort of the role of x and y here interchanged in numerator and denominator, sort of reflecting the pattern that we had in the original equation. So that solves the problem. In the next example, we are given again an equation in x and y, which again you see will be very difficult or impossible to solve for y. In this problem, we are asked to come up with the equation of the normal to this curve at a certain point. So the normal is defined as being perpendicular to the tangent line to this curve at this point. So what we will need to do is we will need to find out the slope of the tangent line to this curve at the point 0, 1. Once we know that slope, we know the slope of the normal, which is the minus the reciprocal of the slope of the tangent line. And since we have the point, it will be easy to write down the equation. So that's what we're going to do. Let's first look at the curve of this function to see how it looks, and again make a rough guess of what we expect the slope of that normal to be. So again, I've pasted the equation of the curve into this function plotter, and I've already picked the right range for this to look at. Let's click the graph button, and you see that's a fairly nicely behaved curve this time. The point we are interested in is the point 0, 1. That's the point here. The tangent line here to the curve at this point is fairly steep, so it has a positive slope. It's difficult to say what it is. It's certainly bigger than 2. So we expect the slope of the tangent line bigger than 2, and the slope of the normal will therefore be the negative of the reciprocal of that number. So let's keep that in mind, and let's go back to the equation. So as before, we'll take our equation and we will differentiate it implicitly with respect to x on both sides. So apply d by dx to both sides. The left-hand side is a product of the function y cubed and e to the negative 2x. So the product rule gives us, well, we first need to differentiate y cubed, thinking of y as a function in x. So we'll need, for the derivative of this first factor, we need the chain rule. So that we differentiate the cube function, that's 3y squared, times the derivative of y, that's the dy by dx. We leave the second factor alone, e to the negative 2x, plus we leave the y squared and differentiate e to the negative 2x in the usual way. That's again a chain rule. The derivative of the exponential function is the function itself, times the derivative of the exponent, that's the negative 2. So that's the derivative of the left-hand side. The right-hand side differentiated is easier. X differentiated is 1. Thinking of y as a function in x, the derivative of y squared we had now several times, that's 2y times dy by dx. I will not solve this equation for dy by dx. What I'll do is I'll right away plug in the coordinates of the point we are looking for. That will make things simpler. So I'm looking at the point 0, 1. In other words, in this equation, I set y equal to 1, and I set x equal to 0. So y equal to 1 gives me gives us 3 dy by dx. E to the 0 is 1. Y cubed is 1. That's a 1. And so all I have left here is a minus 2. On the right-hand side, I got a 1. Since y is 1, I got 2 dy by dx. So what I'm after here is dy by dx at this point. So I want to solve this equation for dy by dx. So I'll take the 2 dy by dx subtract it on both sides, and I get the 3 minus 2 is just 1 here, and the minus 2 I'll get on the other side with a plus 2, and that gives us a 3. So this tells us that the slope of the tangent line at the point 0, 1 is 3. And remember, when we looked at the curve, we did expect a positive slope, and we guessed that the number should be bigger than 2. So 3 seems about right. So that's the slope of the tangent line, but we need the slope of the normal, which is the negative reciprocal of that number. So the slope of the normal is therefore minus 1/3. Right? And since we have the point, we know that the line will go through the point 0, 1, we can right away write down the equation. So the equation of the normal is, well, we'll take y minus the y coordinate of the point is equal to the slope times x minus the x coordinate, x minus 0. And if you want to write this in the standard form, so the equation of the normal is y equal minus 1/3 x plus 1. Okay, and that solves this problem. The last example we're looking at here is slightly unusual and looks different from the previous examples we looked at. So here we are asked to find the derivative of an actual function, and the function we're looking at is x to the x. So it's not obvious that we will need implicit differentiation for this problem, but you will see that we actually do. Again, before trying to find this derivative, let's look at the graph of this function. So I've entered the equation y equals x to the x here, and we're looking at this function on the range from -1 to 5. We'll graph it. You see right away, and we should have probably noted that at the beginning, this function is only defined for positive x. And we did expect, if you look at the graph, that this function grows very rapidly, at least here on the right-hand side. So it has a quite fast growth. But what you also see is that it has a point with a horizontal tangent line with slope 0. So if we are able to find the derivative, we should also be able to find what this point here is. And we see that it is roughly at about 0.25. So the x-coordinate of this point with the horizontal tangent line is roughly at a quarter. So let's see whether we get this when we, after we find the equation of after we find the derivative. So let's now try and compute the derivative of this function. You might first be tempted to apply one of the usual differentiation rules, the one for functions looking like x to the a, or exponential functions looking like a to the x. But note that this function is not of any of these two kinds. It's not a power of x. Well, since the exponent varies, it is not an exponential function with a constant base, since the x here in the base varies. So we need to really come up with a trick here, with a new idea. So let's take the equation y equals x to the x, and the trick here is to apply the logarithm to this equation on both sides. So we apply, and I'll choose to apply the natural log ln. So we get ln of y on the left, and we get ln of x to the x on the right. And now you see why I did this, because according to the laws of the log, ln of x to the x is equal to x times ln x. So in other words, by applying the ln here, I got rid of this exponential, and I made it a product. So if we look now at this equation here, I have again an equation in x and y, where I can think of y as a function in x, and I can differentiate this equation implicitly as we did with the other equations. So as before now, we apply d by dx to both sides. ln of y, we need the chain rule. ln differentiated gives us the 1 over y times the derivative of y, so dy by dx. And the right-hand side is a product, so we'll differentiate x. It gives us 1 times ln x, plus leave the x, differentiate the ln, that gives a 1 over x. Remember, we are after the derivative, we are after dy by dx. Take the y on the other side, we'll get y times ln x plus 1. And since y is equal x to the x, we have now our derivative as being x to the x ln x plus 1. So this is here the derivative of the function. So what we've done here actually is referred to as logarithmic differentiation. And you see it's a combination of applying the logarithm and then carrying out an implicit differentiation. Remember, when we looked at the curve, we saw that the curve has a point with a horizontal tangent line, so we should be able to find the x-coordinate of this point with 0 slope. So that means that's the point where this term here is 0. So that's so set dy by dx equal to 0. Since this can't be 0 here, as we saw from the graph, for example, it must be the point where ln x plus 1 is equal to 0. So ln x plus 1 equal to 0. So in other words, we're looking for the point where the ln is equal to -1, and that's x to the 1 over e. Right, e is about 2.7, so the x-coordinate is roughly a quarter. That's what we expected. So that's the x-coordinate of that point we looked at on the graph. So I hope that these examples have illustrated to you the use of implicit differentiation, that it's really needed to find the derivative of some of these curves.